Good evening and welcome back to your AP Stats lecture notes online. We want to start talking a little bit about how to experiment the right way. We talked about in the last video how experimental setups could be less than ideal, and it was this situation here, going back to the previous slide, where we just take some experimental units, apply some treatment to them, and then measure the response. That is the most simplistic way to set up an experiment in a lab setting where a lot of things are pretty uniform, and a lot of other variables have already been sort of designed out because of the way the lab is set up. That's okay. I mean, doing it something like that, it makes sense. But when you start getting out into the field, you start doing experiments or wanting to find out information or the difference between a couple of treatments for animals or people where not everything is quite so uniform, then this design is not going to help us out. Okay? So we need to do better. We need to find a better way than this sort of simplistic method here. So that's what we're going to talk about today. So a couple of issues with that simple design is that, number one, there's no way to, in a field setting, if we just take some experimental units, give them a treatment, and measure their response, there's no way for us to factor out any lurking variables that might mess with our data. And so, in order to do that, in order to try to factor out some of these lurking variables and to keep them from becoming confounded with our actual explanatory variable, we want to make sure that we're comparing. We got a comparison group. We need what we're going to call a control group that we can use as a baseline comparison to the treatment that we're wanting to see whether or not it's working. Going back to the GPA and dinner with family situation, we examined some other lurking variables that might cause a higher GPA besides just eating dinner with your family. And so what we would do at that point is create two groups. One that was assigned to eat dinner with their family, and the other group that was assigned not to have dinner with their family. And we'll talk about later how that might raise some ethical issues. But anyway, that would be the idea. We would want to apply the treatment of eating dinner with your family and compare it to a group that didn't, so that we can take some of those, types of classes that they're taking, the amount of time studying and things like that out of the equation. So we have some way to compare the actual treatment to. And there may be one treatment, there may be a couple of treatments. That we'll use as many treatments as we need to create an effective experiment. Now, that comparison isn't enough. As you might expect, if we create those two groups to eat dinner or not eat dinner with their family, and then let those subjects decide whether they're going to be in the eating dinner with family group or the not eating dinner with family group, then we're back to the issue that we had in our sample surveys, where your groups are going to sort of self-separate and create two groups that are different in one way or another, and so these lurking variables kind of come back in to our experiment that we're trying to keep those out. So we have to not only create a comparison group, but also get rid of any bias in our two treatment groups by randomly assigning all of those subjects. Now, each subject needs to be randomly assigned. So in an experiment, instead of talking about a random sample, a simple random sample, we're not going to sample it from the population. We're going to randomly assign, so that our experiments are assigned to treatments at random using some sort of chance process. And all of our subjects need to be assigned that way. And so the first type of experiment design that uses this situation. We're going to create two or more groups so that we have something to compare our treatments to, and randomly assigning those groups is called a completely randomized design. And in a completely randomized design, the treatments are assigned to all the experimental units completely by chance. There's a great little section in the book on page 238 that you're going to want to take a look at, where you think you might be randomly assigning, but it turns out you may not be. So I'm going to write this in here. Go check out page 238 in your book and read that. Think about it. You really can't see that. The think about it. Because while in that situation there is a random device being used, you're not creating, if you're not careful, you will not be creating completely randomized groups assigned to your treatments. So do make sure that you check that out. Okay? So in a completely randomized design, the treatments are assigned to all the experimental units completely by chance. This says that some experiments may include a control group which receives an inactive treatment, and we'll talk about what this inactive treatment is called in a minute. You probably already know, or some sort of existing baseline treatment. Now, a control group doesn't have to be given an inactive treatment. There may be a situation where, I don't know, we're testing a new headache drug, and so we want to know if the new drug is outperforming the existing drug, and so we might create a couple of groups that one would take the new drug and the other one would take the old drug, and then try to figure out which headache medicine is working the best there. And so the control group could get an existing treatment already out there that we know works. We're just trying to figure out something works better. So we don't want to get pigeonholed or narrowly, narrow-sighted as far as our control group goes. This completely randomized design can be illustrated pretty quickly in a diagram. And this diagram, you will be asked either on the AP exam, or you will or definitely asked on a quiz or a test in this class to describe a completely randomized design or any experimental design. And there are other types that we'll talk about a little bit later on. And in order to do that, you could write in paragraph form, if you'd like, exactly how you would go through and carry out the experiment, or you can make use of this diagram and shorten a lot of work for you. And so in this diagram, you can first list your experimental units, and you'd want to specifically say how many and what those experimental units are. And then make sure that using arrows and some sort of box here that you're going to randomly assign into 2 groups or 3 groups or 4 groups or however many groups that you need. How many in each group, you want to make sure you include that. And then talk about what treatment each of those groups will get, whether it's an inactive treatment or an existing treatment for the control group, and then the active treatment of what we're trying to test in the other group. But talk about specifically what this is, and then compare your results. Now, you don't want to use this diagram in so much of a, I'll go back, generic method, right? So again, specifically, what are these guys? What and how many? Okay. Here you'd want to talk about number in the group for here and here. And here you'd want to talk about, again, specify what the treatment is that this group is getting. And then last but not least, you want to here list your response. List your response variable. In other words, what are you measuring? Okay. I'm comparing, GPA and the eating dinner versus GPA situation. I'm going to compare the GPAs between the two groups, average GPA, or however you want to go about measuring, but you'd want to specify that. Okay. Now, in this design, which will help save yourself a lot of writing, there is this random assignment. And so this design by itself, this diagram by itself is not enough. We need to come down here and write out how you're going to randomly assign. Okay? And that's what we've done before. Label the experimental units this to this, go to line whatever in the table of random digits, and section off the first, or take the first however many numbers you need, 2-digit numbers, 3-digit numbers, ignoring repeats because we're not going to assign one person to two different groups, and blah, 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 what we've done before. Now, I would encourage you at this point to go and look at, if you haven't yet, look at the example on page 237 in the book. Okay? Go and do that, because it will tell you, it will talk to you about how you would set up in the SAT. Again, we went back and talked about this SAT online course versus not, classroom course, and which one's better review for the SAT. This example will walk you through how to describe out using slips of paper. So a hat method, right? How to describe out using table D, and how to describe out even using technology, using your calculator, using RandInt in your calculator. And so it'll offer up two other alternate methods for this random assignment, and you may like one of the other two better. So you can adopt that method going forward in your homework and your responses on quizzes and tests, which is fine using those other two methods, the hat method or your calculator, RandInt, or technology. But if you're given a section of table D on a quiz or a test or on the AP exam, you'd want to use that method. So be able to describe out the table D method as well. Okay? So anyway, that being said, this would be your design. Okay? And let me show you this in the form of an example or a check your understanding. Okay, I'll give you a chance to write this out first, see how you do. If you need to go back and change once you see what I've done, then make sure that you do that. Okay, so at this time on page 240, there's your check your understanding group here, or check your understanding questions here. Go ahead and read through that, talking about music students and evaluating their performance. Again, there's a footnote alert here in this guy. There's a footnote involved, which means that this actually did take place. So go ahead, stop the video, and try these questions and see what you come up with, and I'll show you what I came up with. Okay. All right, so how'd you do? So the 29 music students, we need to outline a completely randomized design for this experiment. And again, I want to make sure that I state here that it is entirely possible for you to write this out in paragraph form, but man, I wouldn't. Okay, so here's what I came up with. So we're going to start with 29 music students. We're going to randomly assign 15 to one group, 14 to another. And in the group of 15, we're going to assign them to watch and evaluate their videotaped performance in a group setting. So I think the idea again was to evaluate on their own, or to evaluate on their own, then talk about it in a group setting, and then come back and reevaluate. I wasn't exactly sure the setup there, but basically they're going to talk it over in a group and then evaluate their performance. These 14 students are going to be our control group. They're going to be our baseline comparison. So they're going to be assigned to watch and evaluate the videotape on their own. And then at the end of the experiment, we'll bring these two groups together and compare their evaluations to see which ones were a little bit more accurate when compared to, whatever they were supposed to be compared to. okay? But we want to compare how accurate their evaluations are. So this is enough. This would be enough as far as your outline of a design, okay? And yes, you hear Mr. Woodrow's class in the background probably having a pretty good time there. But anyway, now you have to come below this and talk about how you're going to carry out your random assignment, okay? And you can do something like this. Label each student 0, 1 to 29, starting at line whatever. I said 111, doesn't have to be 111. In the table of random digits, take the first 15 two-digit numbers, ignoring repeats between 0, 1, and 29. This should not be new. The corresponding students will make up group 1, the rest will make up group 2. Not the same number in each group, that's okay. We want to try to keep the groups the same number, but sometimes that's not possible, especially if you have an odd number of volunteer subjects. But we can talk more about that later. But that's, again, how you would carry out the random assignment. And the last question here, what's the purpose of the control group? The idea behind the control group, again, is to offer up a comparison between watching and evaluating a performance in a group setting versus on your own. And so when you talk about the purpose of the control group, make sure you do so in the context of the study, right? Everything needs to be in context. Every question needs to be written out so that it is specific to that particular situation, that particular problem, okay? All right, so that's a completely randomized design. So what do we need to be careful of here when we start to set up our experiments, right? A randomized comparative experiment is designed to give good evidence that difference in the treatments actually cause the differences we see in the response. We don't want something else causing a difference in the response beside the treatment. That's where a lurking variable becomes confounded, and we don't want that, right? So there are 3 principles that you'll need to think about, that sometimes you'll need to talk about and need to be aware of when you start to design your experiment. The first one is control. Now, we're going to set up our experiment to try to keep any lurking variables from getting into our results as much as we possibly can, right? And there are other types of experiment design methods that we can employ to help us with that, but we want to make sure that we offer up a control group so that we have this comparison so that any lurking variables that we couldn't design out or that maybe we didn't even think about can be accounted for here too. And so the idea behind the control group here, I don't want you worrying about that just yet, is to make sure that the groups, so basically what we want to do is make sure the groups are the same. We don't want any systematic differences between the 2 groups or the 3 groups or the 4 groups or however many we need. We don't want there to be a difference between the groups. So we want to make sure that they're a good mix and that the 2 groups are the same, so the treatments are assigned to the same types of groups, okay? And again, that'll help us take care of any lurking variables that we haven't thought about. And then once we have that control group, we're going to make sure that we're randomly assigning. We're going to use impersonal chance to assign experimental units to treatments. Again, we want to make sure that the 2 groups, there's not a systematic difference between the 2. So that's going to help us create these equivalent groups as well. And then last but not least, replication. And something that we haven't talked about yet, replication doesn't mean can we do the experiment over again. That's not what we're talking about. Replication addresses the issue of, even if we're randomly assigning our subjects, is it possible that the 2 groups end up being different for some reason? For example, going back to the GPA and eating dinner with your family, if you actually do a comparison, a completely randomized design experiment, you've got a control group, you've got this comparison group, then when it comes time to assign the subjects, is it possible, even through random chance, that we manage to somehow assign all the subjects that already eat dinner with their family a lot to the eating dinner group, and the remaining subjects that don't eat dinner with their family as much to the don't eat dinner with your family group? Is that possible? It is. right? That is certainly possible. So what replication talks about is that we use enough experimental units that when we randomly assign, the likelihood of that happening is not very good, right? So we want to use so many that we eliminate any differences in our groups that might happen even by random chance. So I'll write that in here. The idea is to eliminate the possibility of creating two different groups, even by random chance. Okay? So we use enough that likelihood is very, very small. So eliminate the possibility, probably can't eliminate the possibility, but at least make it very, very unlikely to happen. That's what replication means, right? I don't want to use two subjects and randomly assign one to eat dinner with your family and the other one to not, because two people, they're probably going to be different in some way. But if I use 100, then when I split up 50-50, then there's a really good chance that the two groups are going to be basically the same. Okay, that's the idea behind replication. Okay, so one more thing here to talk about, and then we'll shut it down and wait on some homework for tomorrow in class. But there's an example on page 241 that I want to take a look at with you. And so let's take a look at this example together. As soon as I can bring it up here. All right. So it introduces another sort of twist to our experiments that you probably already know about. So does regularly taking aspirin help protect people against heart attacks? The Physician's Health Study was a medical experiment that helped answer this question. In fact, the Physician's Health Study looked at the effects of two drugs, aspirin and something called beta-carotene. Researchers wondered whether beta-carotene would help prevent some forms of cancer. The subject in the experiments were 21,996 male physicians. There were two explanatory variables, or two factors, each having two levels, aspirin and beta-carotene, and so either they're going to take aspirin or not, or they're going to take beta-carotene or not. And so the combinations of these levels form the four treatments. So there were four treatments. And a fourth of the subjects were assigned at random to each of these treatments. On odd-numbered days, the subjects took either a tablet that contained aspirin or a dummy pill that looked and tasted like aspirin. And so that right there is our first introduction into what's called a placebo, right? Not the first time you've heard that, but anything that's a dummy pill that looks and tastes like the treatment, but does not actually have an active ingredient is called a placebo. And so another vocabulary term that you want to make sure that you understand. And so that's what's going to happen on odd numbered days. On the even numbered days, they're going to take either their beta-carotene or the placebo in place of the beta-carotene. There were several response variables as they looked for heart attacks, several kinds of cancer, and other medical outcomes. After several years, 239 of the placebo group, but only 139 of the aspirin group had suffered heart attacks. This difference is large enough to give good evidence that taking aspirin does reduce heart attacks. Now, this difference is large enough is something that we're going to have to take a look at a little bit later on also. So, great, 100 fewer had heart attacks. What we have to determine later on when we get to our inference procedures is that difference large enough to be significant, something we talked about with our Coke versus Pepsi experiment that we did at the beginning of class. It did not appear, however, that beta-carotene had any effect on preventing cancer. So, unfortunately, that didn't work out so well. And so the issue that I wanted to show you this, and the reason why I wanted to show you this is that we can talk about the three principles of experimental design in this particular health study. Okay. First and foremost, control. was there a control group? Okay, and yes, the answer to that question is yes, there was. There was actually in the form of, there were 4 different groups, and so control was introduced, not necessarily a control group, but control was introduced into the study by having these 4 groups to compare the treatments, right? And you can see here, and it's in your slide as well, this graphic here, right? We've divvied up our 4 treatments together, and that acted as our control, not necessarily a specific control group, but it gave us that comparison that we're looking for in the control principle of experimental design. The next is randomly. It said up here that the subjects were assigned at random to each of these treatments, so that takes care of that random principle. And then last but not least, replication. Again, not can we do it over again, but do we have enough subjects so to where we're pretty confident that the 4 groups are pretty much the same. The only difference is going to be the treatment that they received. And there were over 5,000 subjects, which is more than enough to know that we're not going to get groups that are different from each other, even by random chance. So you'd want to talk about and be able to talk about those 3 principal designs anytime you look at an experiment. Did they control? Did they randomly assign? And were there enough subjects in there to even eliminate random chance as a way of getting 2 groups that are different because of something other than the treatment? Okay? All right, so that's how we're going to experiment the right way. And some things that we want to keep in mind as we set up our experiments. So we'll stop here, not at a check your understanding. There's not one here, so we'll start class off tomorrow with any questions you've gotten, maybe a couple more multiple choice questions to look at as sort of a form of bell work. Homework is in the text. If you want to get started, feel free. If not, we'll have class time tomorrow. Don't forget, I am going to do a homework check for section 4.1, so make sure that those are all ready to go. All right? See you guys tomorrow.